Hello, continuing on with magnetic fields questions. We start here by defining magnetic flux, which we've done many times before. So contextualize magnetic flux through a surface is the magnetic flux density perpendicular to that surface multiplied by the surface area. So won't write that one out. We've done it many times. Part B, figure 4.1 shows a generator coil of 500 turns. With that cross-sectional area, there's the magnetic flux density, and the plane of the coil is perpendicular to the magnetic field. Calculate the magnetic flux linkage for the coil in this position. Right, so they haven't started rotating it yet. They've just put it there. So our magnetic flux linkage is going to be equal to our flux, which is BA, multiplied by the number of turns. So BAN. So B is 0.035, A is 2.5 times 10 to the minus 3, number of turns is 500. Right, so let's do a bit of playing around with this. So 500 times 0.035 is going to be 3.5 times 5, so that's 17.5. Then we need to multiply that by 2.5 times 10 to the minus 3. So let's change that 2.5 into 10 over 4. That'll make things a lot easier. So 175 over 4 is going to be 43 and 3/4. And then we need to, well, knock one of the 10s off. 4.375, 43 and 3/4, times 10 to the minus 2, 4.4 times 10 to the minus 2 Weber or Weber turns, whatever you fancy. You can use either. Right, there's got to be more to this question, and there is. Part C, coil is now rotated about the axis, and there's the variation of flux against time. Explain why the magnitude of the magnetic flux through the coil varies as the coil rotates. Right, so we can say, let's go to our flux equation, BA cos theta. So we've got that, and then we can say where theta is equal to the angle between the coil and the magnetic field. Angle between coil and magnetic field. So then you can say as the coil rotates, theta changes, therefore magnetic flux will change. Therefore phi, make sure you called that magnetic flux somewhere, changes. Cool. State Faraday's law of electromagnetic induction. Right, to save space, I'm just going to say this then. So yeah, Faraday's law is that the induced EMF is proportional to the rate of change of magnetic flux linkage. There we go. The third part, use the graph to describe and explain the variation with time of the induced EMF across the ends of the coil. Right, so we have to describe and explain. We don't have to actually quantify yet. We just need to describe and explain. Right, so let's pick out some basic things on this. So we can say that the induced EMF, which I'm going to use the shorthand epsilon for that, is a minimum at, well, every time we got a maximum or minimum here. So at t equals 0, well, we can say some minimum is also equal to 0. At t equals 0, t equals 0.01. Yeah, there's no multiples of this on the x-axis. These are just straight seconds. 0.02, etc. So that's one thing. We can say there is a maximum at t equals, what's this, 0.005. 0.05. And then we can put in some of the others. What's this, 0.015, etc. Then we could even do i.e. when phi equals 0. So we've got that. We can say that E varies sinusoidally. Can spell it sinusoidally with period. What is the period of this? 0.02 seconds. So just pick out some key things like this. So you're saying where is a minimum, where is a maximum, how it's varying. So put in something to do with period or frequency, and then you'll be fine. Use this to determine the magnitude of the average induced EMF for the coil between the times 0 seconds to 0.005. So up to here where it's cutting the x-axis between these 2 points. So when they're talking about average, they're saying, well, we're allowed to use the deltas in Faraday's law. We don't have to do any clever calculus or anything like that. So we're going to say that is delta n phi divided by delta t. And remember here, they've given us magnetic flux, not magnetic flux linkage. So we want to say what the change in the magnetic flux is. So it's going from its maximum down to 0 in a certain amount of time. The amount of time is 0.005 seconds. Now the maximum, well, we could read it off the graph, but we just worked that out on the previous one, didn't we? What was it? 4.375 times 10 to the minus 2. 4.375 times 10 to the minus 2. Okay, so let's, so that's 5 times 10 to the minus 3. So we're doing, we're doing double this then, aren't we? Yeah, we've got 5 times 10 to the minus 3. Yeah, so we're going to just be doing 2 times 4.375. Right, and that is going to be equal to what? That's going to be equal to 8.75. 8.75, which is 8.8 volts, the two significant figures. State and explain the effect on the magnitude of the maximum induced EMF across the ends of the coil when the coil is rotated at twice the frequency. Right, so when we've got twice the frequency, so we're saying that, I don't really have space to write this, where am I going to put this? Let's just write it up the top here. So we've got that the induced EMF is proportional to 1 over delta t. So if we're doing frequency times 2, that means that the delta t is going to be multiplied by 1/2, which means that the induced EMF is going to be twice as big. That's what we're going to have. So actually quantify that. Don't just say, oh yeah, it's going to be, it's going to be bigger. Yeah, we can actually quantify it. And we know that it's got to go up, because if you're doing it so much quicker, you're spinning it faster, you're putting more energy in. The rate that we're transferring this energy is going to be faster. So we're going to get more oomph in our EMF. So yeah, we're doubling it. Right, so that's the end of that question. I think I'll just do the 2 in this one because these are quite long questions, it seems. Figure 3.1 shows a section through a mass spectrometer. Right, what have we got in the beam of positive lithium ions? I'm just trying to see where all the numbers are, but I haven't said anything yet. Anyway, a beam of positive lithium ions enter the evacuated chamber through a hole at X. Okay, so they're coming in at the bottom. Travel through a uniform magnetic field, which is directed vertically into the plane of the diagram. Vertically into the plane of it. Right, so it's going into the screen, I think is what they're meaning. The ions exit and are detected at Y. Okay. Name the rule that may be used to determine the direction of the force acting on the ions. Right, so Fleming's left-hand rule. Explain why the speed of the ions travelling from X to Y in the magnetic field does not change despite the force acting on the ions. Right, the force acting on the ions is not in the direction of motion of the ions, so there is no work done by the force on the ions. So they're 2 fairly standard questions that come up in, well, even in our classical mechanics stuff when we're doing circular motion. The lithium-7 ions are detected at Y. All the ions have the same speed and charge, and the radius they have marked on the picture. That's what I was looking for at the beginning of the question. They've also given us the mass. Calculate the force acting on a lithium ion as it moves in the semicircle. So this is just classical mechanics of an mv squared over r. So our mass is 1.2 times 10 to the minus 26. Then we've got 4 times 10 to the 5 squared. So that's 16 times 10 to the 10. And then we're dividing by 0.15. Right, so let's change these into some fractions. We've got 6 over 5 is our 1.2. We've got 16. We've got a 1 over 3 over 2, 2/3, but we need to take into account that'll be a 10 to the minus 1 on the bottom, which would make 10 to 11 minus 26, so 10 to the minus 15. So what's all this then? A fifth of 16 is 3.2 multiplied by 4, so 12.8. So 1.28, we've taken a 10 off of that to make it 10 to the minus 14. So 1.3 times 10 to the minus 14 newtons. Calculate the magnitude of the magnetic flux density B. So F is BQV for a moving charge. So we want to get that B is equal to 1.28 times 10 to the minus 14. That's our F. Divide by Q, 1.6 times 10 to the minus 19. And then V was our 4 times 10 to the 5. Okay, so we're getting, oh well, these are all cancelling out then. That goes, that goes, that goes. All of the 10s go. So 0.128 divided by 4 is going to be 0.32. So that's going to be, oh, it just comes out at 0.2 Tesla. Right, those were some really friendly numbers. Then the part C3, the current recorded by the detector is 4.8 times 10 to the minus 9 amps. Calculate the number of lithium-7 ions reaching a detector. Right, so the number of ions is just going to be that divided by the charge. 4.8 times 10 to the minus 9 divided by, was it 1.6? They've all got single positive charge. So, oh, that's 3 times 10 to the 10. 3.0 times 10 to the 10. Right, so far so good. Is that the end? That would be a suitable end to the question. And no, there's another bit. Right, okay, figure 3.2 shows the variation of current I in a detector with magnetic flux density B. Right, so we've got two peaks. These are our lithium-7 ions here. Oh no, peak A, the little peak, is due to ions of another isotope of lithium. These ions have the same speed and charge. Explain the significance of the height and the position of the peak. Right, so the height, let's start with the height then. So it's producing a smaller current. Height is lower, therefore smaller current produced, therefore we've got fewer ions of this isotope. Then what is it telling us about B? So if we've got a weaker magnetic field, our magnetic flux density is lower in order to bend it by the same amount. So we get the same circle radius for lower value of B. So that means that we must either have a higher charge, but they've told us they've got the same charge. So if same charge, they must be lighter in order to be able to bend them more easily. Then must have lower mass. Cool. So, right, that was quite a nice little end on that one. think a lot of people might get caught out by the position one of how to actually explain it. But yeah, weaker field, and we're still bending it the same amount. You have to either have more charge or lower mass. You know, it's a lot harder to bend something which it's got more momentum. It's not going to bend as quickly, so you have to have lower momentum. You know, they're moving at the same speed. So that's what really, I suppose I should have said that here. Must have same charge and speed. They must have lower mass. Because yeah, if they were moving at a different speed, then that would be another thing that could change it. But it's the momentum, isn't it? If they've got a different momentum, if they've got lower momentum, they're going to bend more easily when subjected to the same force. So if we've reduced the force, then we can bend them the same amount because there's less momentum. You know, our force is that rate of change of momentum. So fitting all of your classical mechanics stuff in here by bringing it all back, you know, having our mv squared over r for our circular motion, and that idea that the force is the rate of change of momentum, you know, is critical to a mass spectrometer. Right, two really nice questions. I like those.